Question.
I've seen your hand. Okay.
What is quantum gravity? That's the question? Okay.
So are we live again?
Okay. The question is,
what is quantum gravity?
the question is, what is quantum gravity? And the answer is, I wish we knew. But let me say it more seriously. About 100 years ago, there were two big changes. Some people call them revolutions in our way of understanding physics. The first was the revolution of quantum mechanics. The second was of Einstein's general theory of relativity. Quantum mechanics, before quantum mechanics, the formalism of physics went this way. Things had definite values. For instance, if I wanted to describe the motion of this bottle, I would give it a particular definite shape, a particular definite position, and a particular definite velocity when I threw it up. Okay? We understand that reality is not formulated that way. That there are probabilities for things having particular definite shapes and definite momenta, and there's a fuzz. In a given situation where you only know the probabilities, the position could be here or here or here or here, and you cannot say for sure. Okay? This change in the way of viewing physics is encapsulated within the formalism of quantum mechanics. So this is number one. This is what it means to be quantum, for your description to be within the formulation of the framework of quantum mechanics. What does it mean for it to be gravity? Well, since Einstein, we know that gravity is a consequence of the dynamical nature of space and time. So a theory in which the geometry of space and time is dynamical in a particular way is called the theory of gravity. A theory of quantum gravity would be a theory in which the geometry of space and time is both dynamical but also fuzzy and probabilistic according to the rules of quantum mechanics. Okay? So not only is space-time dynamical, it's uncertain. So theory of quantum gravity is a theory in which we build correctly the structure of both uncertainty as well as dynamics into the geometry of space and time.
Is uncertainty something like Heisenberg's uncertainty?
It's exactly the same. It's the same.
Everyone at the back, last row was there. Go ahead.
A little louder, please.
Very fundamental question.
Yes.
In terms of physics for last 35 years, so in terms of space, when you see space, right, physically, so where does space end? Or is there an end? Or what is the concept of space the way we understand? Right from, have you understood that?
Great. Okay.
Can you just repeat the question?
The question is, does space end? Can it end? Must it end? What can we say about the end of space? What can we say about that issue? Okay, so I'm going to try to answer this with an analogy. Okay, now suppose we have trouble imagining curved space because we live in 3 dimensions, and if space, 3-dimensional space, were to curve, it would curve into some higher dimension, and since we can't imagine that higher dimension, we have trouble imagining this. However, the power of mathematics is that you can put equations to things you can't imagine, but in order to put the right equations, you want to look at a situation where you can imagine to get the right equations, and then generalize the equations. So let's do that. Let's try to imagine curved space in 2 dimensions. This we can imagine because we live in 3 dimensions, and so space can curve in 2-dimensional space can curve it in 3. Okay, so the curved space in 3 dimensions, a 2-dimensional space curving in 3 dimensions is like a rubber sheet. This rubber sheet came up in the answer to a question Jyotishman asked at some point. Now you can imagine the following. See, one kind of rubber sheet is just a flat sheet. This is uncurved space, it has no end, goes on forever. Another kind of rubber sheet is like the surface of a globe. Could be a very big globe. Now suppose you were a very small ant, you were walking on this very big globe. You might for a long time think you were on a flat sheet. But if you walk long enough, you would realize that you could keep going in one direction and come back to where you started. In this case, that's an example of space that has no end. Okay? The third kind of sheet would be like a hyperbola. A sheet that is curved, but nonetheless continues to go on forever. So all three are theoretically, conceptually possible things. Curved space can be without an end, or it can have an end. Both are possible. Now, your question is probably about the space of our universe. Does the space in our universe have an end? I should say that, I'm not 100% sure, but if everything we understand at the moment is correct, the answer is no, there's no end. If the universe in particular is accelerating, there's no end.
The gentleman at the side over there, great, sure, yes, go ahead.
My brain is still stuck to the earlier question about the content of the black hole. We understand when the star ends, it becomes something called as neutron star, that all the electrons of the neutron collides, converge into and become a neutron star, and the mass is still greater. It goes on crushing itself and become a black hole.
Completely right.
So where does the content of the black hole go? What happens to the elementary particle?
Can you just repeat the question
Okay.
for the web guy?
Yeah, sure. The question is, how can it be that, something has collapsed to make up a black hole? Once you've got this black hole, where did it go? Exactly. So now, I'm going to give you two answers. First one, classical, and the second one, quantum. Okay? Classically, this matter shrinks into the singularity. It is like a point or a line of infinite curvature, and we just don't know what to say about it. Okay? However, your question becomes much more pertinent quantum mechanically. Because, you see, classically, nothing ever comes out of a black hole. So, the question of where it went to is not a question that somebody sitting outside will ever have access to. Suppose it went to somewhere in the middle and somehow was stabilized, how would you ever know? Because nothing comes out for you to tell you. However, quantum mechanically, I have explained to you that Hawking radiation happens. Now, a consequence of Hawking radiation happening is the following. Eventually, black holes are not completely black. As a black hole radiates, it loses energy, shrinks, and eventually disappears. So now you see, your question of what happened to that matter is a clear question, because we know the answer. It eventually turns into Hawking radiation. Suppose you send in some stuff, it collapses, you just wait for a very long time. It will have to be a very, very long time, much longer than the life of the universe, reasonable sized black hole. But it doesn't matter. We're doing thought experiments. Okay? You wait for a very long time, what comes out? What was left of that stuff was scrambled into the Hawking radiation and came out. So, from early times to late times, that's what's happened to the matter. It goes in and comes out as radiation. Now, your question is, what happened to it in the middle? When it was still looked like a black hole, what was it? And this is the issue of the entropy of the black hole. You see, what it went to is into one of the many states that make up the black hole. What we understand at the moment is how to count these states. We know how many there are, but we don't really understand the detailed description of the states. But clearly that's what it goes into. It goes into one of these states. So the answer to your question would be to answer the microstructure of a black hole. What makes up this entropy? Okay? Now, within string theory, in certain toy models, we know some things about the answer to this question. But for a normal Schwarzschild black hole, it's fair to say we don't yet know it. And if we knew the answer to your question, we would solve the paradox of Hawking radiation. But it's an excellent question. Well, somebody had asked also about, does time have an end? It could, if the universe was so poof, at the time of the crunch, more or less effectively time would end. Or roughly speaking, at the beginning of the explosion, time had a beginning. Could happen at least in classical general relativity. I'll stop here unless. Yeah. I can't hear you. A little louder.
So what about about the event horizon?
Yes.
The light is stationary. So the density of the light, like the emission of time, the number of photons which will be evolving.
You want to ask why light doesn't build up at the event horizon? That's the question? Why there isn't a build up of light at the event horizon? No, you see, suppose it's actually an unstable situation, not a stable one. It's the opposite of what you're saying. You see, suppose you have light falling into the event horizon. It just goes through and goes into the singularity. So that light doesn't build up. Suppose somehow or the other there was some short-lived observer in the middle of inside the black hole who starts shining torches outside. Okay, he won't have very long to do it, but suppose he does it. Okay, then this light, it doesn't reach the event horizon. He tries to shine it out, but it's all just sucked back into the singularity. Okay, so the only kind of light that builds up at the event horizon is light that is emitted at the event horizon. No, it doesn't orbit around the event. There are no stable orbits lower than a certain radius around the event horizon. And that's not how it works. Stuff that goes from outside just goes in.
Okay, green shirt there and then yellow and blue will come to you. Yeah, green shirt at the back there. Yeah, go ahead. Yeah, you. Go ahead.
What is the depth of a black hole?
What is the depth of a black hole? Well, what we can measure is the area of its event horizon. That gives you a notion of its size. And if in some analogy you try to imagine that this was a sphere of that size, you could say in your mind that the radius that comes from that area would be the depth. So for instance, from this way of giving meaning to that question, if you put all the mass of the sun into a black hole, its quote unquote depth would be about 3 kilometers. It depends on the mass. The size of the black hole depends on the mass. What is string theory? Okay, what is the second question?
The second question is, what exactly is Hawking radiation? Something is emitted, but what is it?
What is emitted? Both excellent questions. Okay, what is string theory? String theory is an attempt to make a quantum theory of gravity. Okay? It's proved remarkably hard to put together these two ideas, A, of quantum uncertainty, B, of the dynamical nature of space-time. The space-time itself is uncertain. It's proved remarkably hard to put them together into consistent mathematics, these two ideas into any consistent mathematics, even if we don't want to get all the details of the real world right. We just want a consistent mathematical model which has both these features in it. That has proved like a remarkably difficult mathematical exercise. String theory is a framework within which you can consistently build quantum theories of gravity. Okay? Within physics we have two kinds of structures, or many kinds of structures, but two of them are frameworks and theories. A framework is a mathematical structure, a mathematical and interpretative structure within which you can model physical systems. So quantum mechanics is a framework. Set of rules within which you can try to model the hydrogen atom or a harmonic oscillator or something else. Okay? The different models for different systems are different, but the framework is just that of quantum mechanics. Okay? Like that, string theory is a larger, richer, very beautiful framework within which it's possible to make quantum theories of gravity. Okay? We don't know whether it's the only such framework or there are many such. This is the only one that human beings have found so far, in my opinion. And that's what string theory is. One second, please. And now, the second question was, what is Hawking radiation? What is Hawking radiation? Yes. If you follow Hawking's calculation, this is how he did it. There's the black hole, and there are particles that live in space-time. Let's say the electron. Now, in quantum mechanics, the vacuum state of a particle living in a black hole is complicated. It's a state in which every once in a while an electron-positron pair pops out of the vacuum. When this popping out happens, the electron-positron pair pops out, it lives for a little while and then annihilates again. Okay? When this happens in flat space-time, this is happening all the time and it doesn't have very dramatic effects. It has some effects, but okay. However, near a black hole, what happens? And this is a caricature of what the actual calculation is, but let me say it anyway. Near the black hole, what happens is this. This electron-positron pair pops out, and then one of these two can go inside the black hole, the other one can come out. Now, because they're separated by this event horizon, and nothing that goes in can ever come back out, they can't come back out and annihilate. So this process, which would have these virtual, almost imaginary electron-positron pairs, suddenly creates two real electron-positron pairs. Now it turns out, and this is part of the details of the calculation, that when this happens, the thing that goes in carries what an outside observer would see as negative energy, whereas the thing that comes out with positive energy. So effectively it's this like bubble of electron positron pairs popping up all over the vacuum, some negative energy parts of which go inside the black hole lowering its energy, and positive energy ones come out. This is how Hawking did his calculation. Okay, now you see from this description that if this is the way things work, all that the details of the radiation depend on is what's happening near the event horizon. And this is what led to Hawking's information paradox. Was this clear? Okay.
Okay, before we will come back, but we also have around 100 people who are
Yes,
watching
sir.
online.
Yes.
And there are some questions from there as well. So, can gravity be mediated by two or more kind of interactions instead of only one?
Can gravity be mediated by two or more kinds of interactions instead of only one? Well, there are many ways of interpreting that question. One way of interpreting that question is this: can there be other long-range forces that mix with gravity? You could have, for instance, a massless scalar field, like the dilaton in string theory is a massless scalar field that affects long-range gravity and would in some sense violate an equivalence principle. If the question is, however, the more interesting one is of whether you could have two massless spin 2 particles that are simultaneously dynamical and give you gravity, the answer is probably no. Probably no.
All right, let's go back. It's blue and yellow, but there's red, blue and yellow there. Louder, please, louder. We can't hear you.
You're talking about the entropy of black holes. What are we talking about? Which part? I don't think I use the words ghostly auxiliary space, but anyway, go on. The emergent, the boundary theory. Yes, thank you. Yes, go on. You want to know more about that? Okay. I have to give you then 1 minute on the structure of the ADS CFT correspondence. Okay. See, I told you in answer to this boy's question that string theory was a framework within which it was possible to build consistent quantum theories of gravity, and this is going to have to be very fast, but anyway, for what it's worth. The one really satisfactory, completely satisfactory quantum theory of gravity we have has been constructed using what's called the ADS CFT correspondence. Now I'll tell you the structure of this correspondence. The structure goes this way. The answer to the question, what is the complete quantization of quantum theory of gravity in a particular 10-dimensional space called ADS 5 cross S5? The answer to that question is a quantum field theory, a non-gravitational quantum field theory that lives in 4 dimensions. Now, this non-gravitational quantum field theory has a parameter called n. And you can take this theory and solve it in an approximation in which n is taken to be very large. And solve this theory in a power series expansion in 1 by n. And the leading term in that power series expansion in 1 by n gives you a solution of this theory, in which in that solution of this theory, you see that solution is given in terms of a 10-dimensional space-time with dynamical space and time. Okay? So the ghostly auxiliary space is the 4-dimensional quantum field theory. There's no mention in the theory of 10 dimensions or dynamical space-time. The gravity theory is the solution which comes out. Now this solution comes out in an expansion in this parameter 1 by n. It's precise when n is infinity. When n is a million, it's approximately precise. The space-time will fluctuate in a way that you think of as quantum mechanics. When n is 2, has no reality. Okay? So at least within this mathematical model, the only real thing is this ghostly auxiliary space. Space-time is an illusion that comes out of our approximation and gets worse and worse. Quantum gravity is the fact that the approximation is becoming worse. And when you go to n equals 2, there's no space and time at all. Okay? This is the structure. Now, I'll just say one more thing. Now, locality in this space-time is a derived concept because the theory is completely local in this 4-dimensional space. Locality, to the extent that it happens, either happens or not from your solution. Classically, large N limit, everything completely local. Quantum mechanically, the structure of this locality is very much modified. And this is what allows information to come out.
You said the area of the event horizon increases or stays the same.
Classically.
Then you said the black holes are dark matter.
Excellent. So there's a contradiction. The contradiction has its roots in the fact that the first theorem was a classical theorem. Within classical general relativity, the area of an event horizon can only stay the same or increase. However, quantum mechanics violates that postulate. Now, you see, this violation does not violate the second law of thermodynamics, because when the event horizon decreases, it decreases because the black hole is emitting radiation, and the radiation itself carries a huge deal of entropy. Okay? So it still continues to be true that the net entropy of the universe increases, even though the area of the black hole decreases. This is a good question, so let me say one more thing about it. Okay. That doesn't matter. Maybe you remember the formula I gave you for the entropy of a black hole. No, that was the formula for the temperature. Sorry. Yeah. The formula I gave you for the entropy of the black hole, all I want you to remember is that it had a 1 by h bar in that formula. Now, a quantum theory becomes classical in the limit h bar goes to 0. Okay? So, in the classical limit, the entropy of a black hole is larger than anything else. So, it's impossible for net entropy to increase if the entropy of the black hole is decreasing. This is why in the classical theory, the area of the event horizon had to only increase. In the quantum theory where h bar is finite, this can decrease but be compensated for by other forms of increase, and that's what happens. Is this clear?
Yeah.
Thank you.
If you said that even light can't escape black holes,
Yes.
gravity does affect the light. So shouldn't it be possible that can't we gather enough light in one place? So the gravity should affect that also. Can't it also make a black hole then?
Yes, it can. It's a very good question. The question is, can we make a black hole by the collapse of light? And the answer is yes. Consider a shell of light, maybe shell made using lasers, a spherical shell of light, which is very thin and focused, so it will all come together at a point. If you can make that shell thin enough and energetic enough, you can make a black hole. In fact, there is a solution of general relativity that describes the formation of such a black hole by another great Indian general relativist guy from Gujarat, Professor Vaidya. The Vaidya solution describes precisely what you're talking about. So it can happen. I don't know if it does happen, but it can happen. Yes. Yes.
You said when the star runs out of fuel, it explodes into a supernova and forms a black hole. How does it get the energy to explode?
You see, what happens is that the star is very big. Oh, sorry. The question is, once a star has run out of fuel, it seems like it's run out of all energy sources. How then can it have the energy to make a supernova? Right? The thing is that a star is very big. When it runs out of fuel, it starts collapsing. Now that collapsing turns the potential energy of that stuff into heat. So it makes the black hole makes the star very hot. Now that hot thing does all kinds, that heat does all kinds of, firstly it's very hot. Secondly, that heat triggers new fusion reactions that would be impossible at a cooler temperature. So there's sudden new spurt of energy. So it's some very complicated process involving new sources of energy that causes the explosion. Yeah. In the question is, I'm claiming there's a black hole information paradox. What does that statement mean in particular? What is the definition of information by which there is a paradox? Here, in the context of the black hole information paradox, the definition is very simple. It's simply this. You see, in quantum mechanics, you have what's called a pure state. Okay. Now, within quantum mechanics, a pure state, something that has as definite knowledge of a state as is possible within quantum mechanics, can only evolve into another pure state. There are other notions of states in quantum mechanics called density matrices, okay, where you have one pure state with a particular probability, another pure state with another probability, and so on. Okay? Within quantum mechanics, at a fundamental level, you cannot have pure states evolving into density matrices. Okay? Hawking's calculation seems to suggest that in the collapse of black holes, pure states evolve into density matrices. Okay? Now, this is called the information paradox because of the following. Given a pure state, given a density matrix, how near to a pure state it is can be computed by computing the entropy trace of rho log rho of the density matrix. Okay? The entropy of a pure state is 0. The entropy of a very mixed state is 1, or some large number. Sorry, and the statement of unitarity is that the entropy does not change. So the information paradox is that it appears that entropy is increasing with an actual evolution, which cannot be. All right, I'll just. The question is, what kind of experimental data is relevant to understanding quantum gravity? Can LHC or other collider physics experiments help? You know, until we know the answer, we're not sure, but it sounds very unlikely. A naive estimate of the kind of energy scales we need to probe quantum gravity in collider experiments is like 10 to the 16 or 10 to the 17 GeV, and we are at what? 10 to the 3 GeV. Okay, so there's a huge gap, 10 to the 14, 10 to some, doesn't seem likely. You know, there are people keep coming up with weird scenarios in which it might be large extra dimensions, blah blah blah, but these sound unlikely. So unlikely that collider experiments will shed immediate light on quantum gravity. Very unfortunate. No. You see, white holes are mathematical solutions of general relativity, but they are solutions of general relativity that require a particular initial condition, and it seems very unlikely that our universe had that initial condition. A black hole that is formed by collapse, which is the mechanism for black hole formation in our universe, does not have that white hole part. See, you are referring to the fact that if you look at an internal black hole, it has both a future event horizon and a past event horizon. Real black holes formed from collapse do not have those. Okay? It does not seem that that is relevant to solving that. It doesn't seem to me that that's relevant to solving that question.
At the back there.
I don't even know what the theory is. I can't comment. Sorry.
Okay, yeah, the back there.
So, as it actually says that at an event horizon, your virtual particle one which goes inside the black hole and one which radiates outside, and it becomes into a real particle, right? Or does that happen that real particle could again collapse inside the black hole?
It could, but it doesn't have to. In particular, you know, this real particle that's going out sees a potential barrier, and there's some probability called the gray body factor, and there's some amplitude that it will reflect off that potential barrier and come back into the black hole, but there is some amplitude that it will not. So those that make it out are the radiation. Yes. Oh, sorry. I'm sorry.
If nothing can escape a black hole, if none of light can escape, then how is it possible for something to be radiated?
You see, the fact that the statement that nothing can escape a black hole is a classical statement. Within classical mechanics, nothing happens. But I try to explain to you how it happens in quantum mechanics. You see, there is this pair production. Now, this pair production, precisely because nothing can happen in a black hole, leads to radiation. Because one guy goes where nothing can escape, the other guy goes where where it can. So you may say, it's not really coming from the black hole. It's coming from the neighborhood of the black hole. But it's extracting energy from the black hole. Eventually it is radiating.
So, you told that during the lecture that microscopically and fundamentally, all the particles are reversible.
Yes,
Why does irreversibility occur in microscopic scale?
that's a very good question. The question is a deep one. The question is that the basic laws of physics at the ultimate microscopic level are time reversal invariant. If a motion can happen forwards, the same motion can happen backwards. If you looked at the molecules moving, and you looked at a few of them, you cannot tell whether they're moving forward and backward or backwards. Yet if we look at the real world, it's very clear, right? You know, a cup of tea you put there, it cools. It never happens that you put a cool cup of tea and it becomes hot because that never happens. Okay, this in the end must be a statement about the special nature of initial conditions that our world is in. You see, let people who've investigated this issue find the following. Suppose you start with a state of special states and allow the state to evolve either forwards or backwards in time. Okay? From these special states, in either direction, the entropy will always increase. It will increase forwards in time or backwards in time. However, these special states are very special. Okay? So, imagine that the universe, or at least the part of the universe that concerns us, started in one of these special states some time ago. Because we are this side of the special state for it, entropy is increasing like this. Okay? That's the best I can do. There may be a much better, deeper and more interesting question. This is a very interesting question. It's a kind of question that leads to, it's very interesting, it's led, people have asked it for 100 years and made no real progress. So it's not a question you should work on, and just to warn you. But it's a very interesting question, and there may well be a better answer than what I'm giving you. There probably is, but I don't know what it is.
Shiraz, I've just completely forgotten that there are people here.
Yes.
So about the black hole and the there is, you said the dark energy entering into it. So what does exactly happen to that energy? Is it like coming out from the other side, and the black hole is like a tunnel?
Okay. The question is, what happens to the energy that enters into a black hole, perhaps the energy that makes it up? Does it come out from the other side? Is there a wormhole between these two sides? Now, you see, there are two kinds of black holes. A black hole of the kind formed from the collapse of a star does not have another side. Okay? So, it cannot come out from that side. This just doesn't exist. And in fact, to the extent that we understand it, the energy stays inside the black hole until it escapes out by Hawking radiation. Okay, so just that. However, there are other kinds of black holes, sort of like these eternal black holes that have a second asymptotic region. Some of these in model systems can be created by pair production. Even in such a situation, you cannot have real stuff, you cannot have real particles getting into a black hole and coming out of the other side, at least classically. That cannot happen. There's lots to say, but it's a good question. But
So how do you determine which type of?
the process of formation of the black hole determines which kind it is. Almost any classical formation, almost any classical formation process forms the first kind of black hole. You need a very quantum process to form the second.
Okay, it's already 1 o'clock. Last few questions only. Okay. Quick question, quick answer. Yeah, go ahead, Grace. What is multiverse?
What is the multiverse? But he wanted a quick answer. Okay, I'll tell you very quickly. You see, there's a kind of space called de Sitter space, which is constantly expanding in an accelerated way. If it happens that you are in a de Sitter space and you're in a false vacuum, then it could be that you make a tunnel to a true vacuum, and you form a bubble of that true vacuum, and the true vacuum then starts expanding. Now, in normal space, if a true vacuum starts expanding, it eats up all of space. But now in de Sitter space, when this happens, de Sitter space is expanding even faster than the bubble can expand. So this bubble keeps expanding, but it only occupies a finite fraction of de Sitter space. Now you could have another bubble forming here. That also expands, but these two bubbles are being taken away so fast by de Sitter space that they never meet each other. So you could have an infinite number of such bubbles, all sitting in the same de Sitter space. Each of these bubbles could be, in principle, the Big Bang for its own universe. Okay, this set of bubbles and bubbles and bubbles is called the multiverse. Whether it exists or not, God alone knows. Yeah.
What is the future of the black hole? Will it ever die?
By Hawking radiation, it emits radiation and dies.
Okay, I'm going to take this kid's last question and then we can wind up formally. And yeah, go ahead.
Excuse me, what is M theory?
What is M theory? Within string theory, there is a particular strong coupling limit in which the equations of motion of string theory become those of what is called 11-dimensional supergravity. That's M theory. M theory is a fancy name for one of the structures that appears within string theory, which is this consistent way of building quantum theories of gravity.
Okay, I think we should formally thank Shiraz. He's taken a lot of time and I'm sure that we can continue questions for hours.